How is it 90% of sessions, or what this actually mean? When people say 90% of session use Quick, they do not mean every router, ISP, and device in the world uses Quick. It means for apps that support Quick, YouTube, TikTok, Facebook, Gmail, etc., 90% of their traffic successfully negotiates Quick instead of falling back to HTTPS or TCP. This depends entirely on the server, Google, Meta, ByteDance, the client software, Chrome, YouTube app, the network allowing outbound, UDP 443. Your personal devices do not affect the global percentage, they just determine whether you personally use Quick or fall back to TCP. Does your router or laptop support Quick? Your laptop, Windows, Chrome, Edge, Firefox, yes. Modern browsers fully support Quick, IETF Quick to HTTP 3. Your converged router, yes, almost definitely. Home routers don't need special Quick support. Quick is user space and end-to-end between your browser or app. The CDN server routers only forward UDP port 443, which virtually all home routers do. So your router can forward Quick even if it doesn't know Quick. TNT mobile data and Huawei phone support Quick? Yes, very likely. Clues: Smart or TNT adopted Google Quick traffic since 2021. Mobile apps, YouTube, TikTok, FB use Quick by default. Huawei phones, Chrome Web View supports Quick. Exception: if your mobile data momentarily blocks UDP port 3, congestion, or CGNAT issues, Quick will fall back to HTTPS or TCP. How do I check my connection is using Quick? So on Chrome, visit Chrome //net interna /http /number http2, and then play a YouTube video, looks for http3, and there's also a specialized website that you can check to do that. How often do CDN hosts switch in PH for YouTube or Google traffic in PH? CDN or edge load balancing happens constantly, every few seconds or minutes. Your device can be redirected between Manila, Google, POP, Cebu POP, Davao POP, Singapore backup POP, Hong Kong fallback POP, local ISP caches, Converge, PLDT Globe. When does switching occur? Congestion spikes, cell tower changes, mobile data, ISP routing changes, BGP update, switching from Wi-Fi to mobile, quick connection migration built in. So that's in order. Whenever you have congestion spike, you switch, or your device can be redirected between Manila, Google POP, Cebu, Singapore, Hong Kong, in that order. So as you can see, it goes from near to the farthest. How does CDN switching work in code? CDN selection is not done by front-end code like React or Angular or Next. Instead, it's done by DNS load balancing. YouTube.com to DNS 142.251.xxx.xxx nearest Google CDN. Then, quick connection migration. Quick automatically detects path change. Own underscore path equal 10.0.0.5 colon 45678 142.251.10.5 colon 443. Then new underscore path equal 10.0.0.5 colon 45922 to 142.251.10.5 colon 443. Then quick performs path underscore challenge, path underscore response, idle underscore timeout reset. No TCP style reconnect is required. Third, HTTP or 3 alt SVC advertisements, alt -SVC h3 equal code new dash edge dot youtube.com colon 443. Browser migrates automatically. 7. Do React, Angular, or Next.js use Quick? No. Front-end frameworks never interact with Quick directly. Why? Browser hide Quick inside fetch, XHR, web transport, HTTP or 3. Front-end JavaScript cannot open raw UDP sockets. Quick live inside the browser network stack, not user code. So React or Angular code like fetch argument slash API slash video becomes quick HTTP3 if servers support it, TLS or TLP if quick fails. Framework code never calls a UDP bind or quick handshake. How are your STAN questions related? What does just client to CDN means versus STAN? Quick video apps, YouTube, TikTok, Netflix is client to CDN. No STAN, no P2P, no NAT traversal. Always server quick. STAN only used by peer-to-peer applications like WebRTC calls. Needed because two devices behind NAT must connect to each other. So, feature P2P, quick YouTube? No. WebRTC or STAN? Yes. Feature needs STAN, quick YouTube? No. WebRTC or STAN? Yes. So, runs over UDP 443? Quick YouTube? Yes. WebRTC or STAN? Yes. Feature not traversal logic? Quick or YouTube? Built into Quick? Keep alives? WebRTC or STAN? STAN/I/turn. How can multiple STAN transactions exist over TCP? Meaning, a TCP connection can carry many STAN requests at once. Each has a unique transaction ID. Responses match IDs, not ports. This has nothing to do with Quick because Quick apps don't use STAN. So, TCP could have multiple sessions, each with unique transaction ID. So, this transaction ID will be important in STAN as well, using turn, which we will discuss in the future video. And this has nothing to do with Quick because Quick apps don't use STAN. Summary: your devices and PH networks overwhelmingly use Quick for YouTube, TikTok, FB, unless UDP or 443 is blocked. Quick is automatic, handled by browser or network stack, not front-end code, and STAN is not used at all for video streaming. Facebook, the website, is equal mostly HTTP3 quick. So when you load facebook.com homepage in your mobile or laptop browser, facebook.com homepage, news feeds, reels, images, videos, profile pages, these all use HTTP over 3 over quick UDP or 443 if supported. Your test confirms Facebook CDN support HTTP or 3 and your connection used quick. So the browser content itself, HTML, CSS, JS, images, API calls is mostly quick. But Facebook Messenger traffic is different. Here's the precise breakdown. Number 2. Facebook Messenger text messages equal not quick. Messenger text chats still use a long-lived WebSocket over TCP or TLS. Protocol WSS WebSocket secure. Transport TCP port 443. Reasons: WebSockets require TCP semantics for ordering plus reliability. So even if Facebook.com supports HTTP3, Messenger messages still ride on TCP. Why? Quick is great for request or response and streaming, but Messenger uses persistent bidirectional real-time session channels, traditionally based on WebSocket over TCP. Facebook did not migrate Messenger to pure quick as of 2025. Summary table: Facebook feature, facebook.com browsing, transport, quick, HTTP over 3, notes, HTML, CSS, JS, images, feed. Facebook feature, Facebook video reels, transport, quick, HTTP3, notes, buffered video chunks, Facebook Messenger text, transport, TCP, WebSocket or WSS, notes, long-standing persistent channels, Facebook feature, Messenger voice or video calls, transport, UDP, WebRTC, stun, turn, ICE, notes, peer-to-peer if possible. Facebook feature, fallback mode, transport, TCP plus HTTP2, notes, happens on networks that blocks UDP /443. Why does Messenger does not use Quick for messages? Because Quick is connection oriented, client to server, not ideal for bidirectional push chat sessions, supported only by web browsers, not by app SDKs universally. So Quick are supported only for web browsers. So whenever you use web browser, you probably use Quick, not the Android SDK. Harder to load balance for chat microservices. Messenger already uses MQTT over WebSockets, which is easier for load balance for chat microservices, which runs on TCP 443, which guarantees packets ordering needed for chat delivery correctness, timestamps, reactions, read receipts. And about YouTube, the test in YouTube will show 0 to RTT quick handshake use, HTTP3 use for all connections, video streaming chunks delivered over Quick. YouTube that does not use WebRTC for streaming, it is purely client to CDN. So final, facebook.com website equals quick HTTP3, Facebook video quick HTTP3, Messenger messages equal TCP WebSocket /WSS messenger calls equal UDP. WebRTC stan /turn /I. So the website uses Quick but chat messages do not. Stan attributes are encoded in a TLV arrangement, a technique used by several other internet protocols. The type and length portion of a TLB are each 16 bits and the value portion is variable length, up to 64 kilobytes if supported, but padded to the next multiple of 4 bytes. Padding bits may be any value. Full diagram. So IP header, then UDP header, then stan header, we have 20 bytes. Message type 16 bits, message length 16 bits, magic cookie 32 bits, transaction ID 96 bits. So this will not change, the transaction and magic cookie. The only thing that will change here is the message type and the stan attribute. So this will be relevant in the future video or in the later part because we will use this in ICE. So you can see we have 20 bytes, 96 bits plus 32, 16 plus 16. So how much is that? 96 plus 32 plus 32, 64, 160 divided by 8. So that's 20 bytes. That's where you get the 20 bytes. Stan attributes, you have type length value, padding 0 to 3 bytes to make way for odd number because you want to make sure that it's even. So why this matters? Relating to our previous questions, stan lives after UDP, before application logic. Attributes are the payload that NAT devices use to extract your reflexive address. So the attributes are kind of like the extensions, but there's actually another extension that ICE will use. But this is the payload that the NAT use to find a reflexive address that will be used as a server by the client. Now, padding ensures NATs and WebRTC stacks can parse attributes efficiently. So it's kind of like a way for the hardware to easily process that because it's even. Quick does not use stan, client to CDN only. Stan is only for peer-to-peer, not traversal. WebRTC, games, VoIP. So this is what you use in voice call or video call. So the stan message you sent earlier, the diagram posted shows 20 byte basic stan header followed by attributes if any like this. Inside stan, all the real meaning, map address, username, nonce, fingerprint, etc. lives in attributes. So the username that you will technically have to use to be able to contact the server, what's your username, because you usually need to request to connect to other peer that also support Stan to be able to connect them directly. So you will usually need username, nonce. This nonce is kind of like a unique password, fingerprint, etc. This is located in attributes. So in attribute type, the 16 bits. So we also have TLB in attribute type, length, value, and padding. In 16 bits, this is where you have the type. 16 bits for length, and attribute value is actually variable. So as you can see in stan attributes, it's variable. It's not like 20 bytes, just like the message length. You the reference to the value portion being variable length up to 64 kilobytes. This is exactly this attribute value section. Why must stan attribute values be padded to a multiple of 4 bytes? Because stan was designed to be processed very efficiently by hardware and low power NAT devices. So again, this is the reason why a stan attribute values be padded to a multiple of 4, which is we saw in the stan attributes. We have a padding after the value because stan was designed to be processed very efficiently by hardware and low power NAT devices, because remember, the NAT has low powered hardware. Many network chips expect 32-bit alignment, 4-byte boundaries, so it also helps with generality to be able to work with different NATs. NAT padding makes parsing harder and slower. So if we didn't pad that the NAT or the response from that server, this is already slow mechanics. So NAT padding it will even make it slower. So if an attribute has 3 bytes, stans adds 1 padding byte. If an attribute has 7 bytes, stan adds 1 padding byte. If it has 8 bytes, no padding is added. This is exactly what they mean, padded into the next multiple of 4 bytes. Padding bits may be any value. The padding bytes are ignored by the parser. So where this fits in the diagram. So we have stan header, which has message type, magic cookie, transaction ID, attributes if any. Every attribute inside that bottom region has its own type, has its own length, has its own value, and it's padded to 4 bytes. So any attributes, because every message type, you have different message type for different request or response depending on how your stan configured. So each of that configuration will have its own type, length, value, and padded to 4 bytes. So example, attribute type, username, length 5 bytes, value Alice, padding is 3 bytes. So how this relates to NAT behavior. So because you have length of only 5 types so as you can see, you can definitely see how much padding you will add in the attribute TLV. Because if the length is, for example, 5 bytes, since you need to pad that in 4 byte structure, you will need to add 3 bytes. So how this relates to NAT behavior? UDP NAT timers, fragmentation issues, stan transaction IDs, binding request, allocation, create permission, channel bind, etc. Stan attributes are how these requests are encoded. Example, stan method binding, important attributes, x mapped, address, sor map address, allocate. So here This method is the type. For example, you have type banding. This is the available attributes for that. XMAP address, SORMAP address. This is what you relay or respond as an address of the available server or peer that will be used. Allocate, requested, transport, lifetime. So it will provide the requested, the transport that the peer will be using. Send or data, the data attribute. So if you have send or data type message, you have data attribute, channel bind, channel number, peer address. Every one of those attributes use this exact TLV type, length, value, variable length, padding. So type, you have 2 bytes of type, which is a 16 bits. Length, 16 bit again. So this is what you get, where you get the value of 5 bytes, etc. That will determine how much you would pad. So the statement is describing the binary format of that attribute section. So how this connects to STAN over TCP or UDP? Multiple pending STAN transactions can be supported over TCP-based connections. STAN messages need transaction ID 96-bit, several attributes, padding rules. So a STAN, whenever you're using STAN, you're gonna use the several attributes to communicate with the server. The transaction ID and a magic cookie will stay the same for as long as it's the same transaction, whether it's request or response. Whether STAN is over TCP or UDP, the format is identical. The attributes follow the same 4-byte alignment rule. So even if you fall back to TCP, it still follow the TLV and the format alignment rule. The only difference, TCP solves fragmentation, packet boundaries preserve because it's oriented and ordered. UDP fragmentation breaks not because port numbers exist only in the first fragment. That's why you cannot create like multiple sessions the same way with TCP. The attribute padding rule remains the same in both classes. Final summary, the picture shows the STAN header plus attributes. The value portion is variable length, refers to the value field of each attribute. So the value portion of the attribute is a variable length. STAN requests every attribute's total size. So each attribute, it requires the total size to align to 4 bytes. That's why we pad that in the attribute header. Extra padding bytes are added so parsing is easy for NAND devices. So it makes it easy for NAND devices wherever you are in the world. So again, it is in user space. This is part of the binary encoding rules from RFC 5389. These attributes carry the useful STAN data. So the STAN data will be on attributes, the map address, username, nonce, etc. So again, if it's allocate binding, that's where you get the STAN data depending on message type. So you can see here basics, STAN header in attributes. So usually you need to have attributes, but you can choose to avoid that. So these are the STAN methods: binding, allocate, refresh, send data, create permission, channel bind. And these are the methods. It's 12 bits. Message encoding type, request, indication, response, response error. So we have transaction ID, magic cookie, 32 bits, message length, etc. STAN messages always begin with 20 bits and are usually encapsulated in UDP, although TCP is also allowed. The message type field gives both the method binding as well as class request, response, error, or success. The transaction ID is a random 96-bit number used to match requests with responses or for the debugging in the case of indications. So this transaction ID is used to match each request and response. So you can imagine a client will send a request to the STAN server and will receive this same response. It's useful for debugging and in the case of indications, for the request indication response error message type encoding. Each TAN message can hold 0 or more attributes depending on the particular usage of TAN. So it can add, it can choose to have not, it can choose to not have the usage depending on how it will be used. The same attribute type may appear more than once in the same STAN message. So in the same message, the same attributes could be provided twice, such as the SOR message or SOR address or relay address, etc. Although only the first is necessarily processed by a receiver. So the only first attribute, so let's say you have the duplicate attribute, the first attribute will be processed if it has redundant, because what would you do with the same attribute, right? And it will have the same transaction ID for request and response. Attributes with type numbers below 0x8000 are called comprehension required attributes, and the others are called comprehension optional attributes. So for attributes below the number 0x8000 are comprehension required attributes, and other are comprehension optional. So there's a required and there's also optional attributes. If a STAN agent receives a message containing comprehension required attributes it does not know how to process, it generates an error, which is part of the message type encoding response error, which is 1-1. Most of the attributes defined to date are comprehension required ISP. Of course, the optional is just optional. So most of the attributes that we define today that is being used by STAN is our comprehension required. RFC 5389 defines a single STAN method called binding, which can be used in either request or response or indication transaction for address fixing and keeping NOT bindings current. So there is a unique STAN method which is in the message type called binding, which can be used for request and response, because usually that's different type, right? So yeah, this type of attribute or type of method or type of message can be used in request and response and for indication as well, for address fixing and keeping NOT bindings current. It also defines 11 attributes in table 7.2. So table 7.2 STAN defined in RFC and sometimes called STAN2 replaces classic STAN. These 11 attributes may be used by a STAN2 compliant client or server. So again, this need to be the client and server communicating. There must be a server and the peer must support this STAN, or it must be compliant by STAN2. So name, map address, value 0x0001, purpose or use. So these are the attribute type. Okay, so it contains an address family indicator and the reflexive transport address for IPv4 or IPv6. So it contains the address that will be returned to the client. Username 0x0006, username and password. Used for message integrity checks up to 513 bytes. So this is in the attributes as well. It's a user type. It could contain up to 513 bytes. It contains the username and password used for message integrity if you want to make the process secure. So it's important in WebRTC application. Message integrity, message authentication code values understand message. Error code 0x0009 contains a 3-bit error class, 8-bit error code value, and a variable length textual description of error. So there's a description of error depending on the 3-bit error class and the 8-bit error code value. Unknown attributes 0x00A used with error message to indicate the unknown attributes, 116-bit value per attribute. So again, this is all in the type of the attributes. So this is the value you would put in the type of your attributes. It's either 0x000A, 0x0009, etc. Realm 0x0014, it indicates authentication realm named for long-term credentials. We will see this later. Nonce 0x0015, non-repeated value optionally carried in request and response. So it's a non-repeated value that could be used for request and request to prevent replay attack, to make sure there's only one request and response for that and not multiple request and response. Zord map address 0x0020, Zord version of map address, software 0x8022, textual description of the software that sent the message, like manufacturer and version number. Alternate server 0x8023 provides an alternate IP address for a client to use, encoded as with map address. Fingerprint 0x8028, CRC32 of message, Zord with 0x5354554E, must be last attribute if used optional. Address and port translation behavior. So there has been considerable variation in the way that NATs operate. Most of the details relate to the specific of the address and port mappings. One of the primary goals of the Behave Working Group in IETF was to clarify the common behaviors and set guidelines as to which the most appropriate. To better understand the issues involved, we begin with the generic NAT mapping example in 7.5. A NAT's address and port behavior is characterized by what its mapping depend on. The inside host uses IP address port capital X small x to contact. So these are the referring to this as STAN client with addressing information capital X X, which is this, is often interested in determining capital X1 tick small x1 tick, called the reflexive transport address or map address. So this is actually where we can base our STAN as well. This will be the reflective address shown in our attributes. A STAN server at capital Y1 small y1 includes the reflexive transport address in a map address attribute in a STAN message returned to the client. So this is where you get the transport, that map address in the map address attribute. The map address attribute holds an 8-bit address family field, a 16-bit port number field, and a 32-bit or 128-bit address field. So it has a family bit, a 16-bit port number that will be returned, and its IP address depending on whether it's IPv4 or IPv6, indicated by the address family field, 0x01 for IPv4, 0x02 for IPv6. This attribute is included to remain backward compatible with classic STAN. The more important attribute is the Zord map address attribute, which holds exactly the same value as the map address attribute, but Zord with the magic cookie value for IPv4. So this attribute, Zord map attribute, holds exactly the same value as the map address attribute, but actually Zord in IPv4, or a concatenation with the magic cookie and transaction ID values for IPv6. So this Zord map address attribute is actually used alongside with the magic cookie. So it's actually Zord for IPv4 and then concatenate for IPv6 and transaction ID. The reason for using Zord values in this way is to detect and bypass generic ALGs that look through packets and rewrite whatever IP addresses they find. So to avoid like intercepting it along the way and then rewriting the IP address. Such ALGs are very brittle because they rewrite information and protocols such as STAN require. Experience has shown that Zoring IP address in the packet payload is usually sufficient to bypass such ALGs. So Zoring the IP address in the packet payload are proven to bypass such ALGs. A STAN client including most VoIP devices and soft phone applications such as Pisua is initially configured with the IP addresses or names of one or more STAN servers. So if you have a client including VoIP devices and soft phone, it's usually used for like call center applications such as Pisua. It's actually initially configured with an IP address or names of one of more STAN servers it will communicate to. It is desirable to use STAN servers that are likely to see the same IP address as the peer to which the application ultimately wishes to talk. So again, it is desirable to use STAN servers that are likely to say the same IP addresses as the peer as to which the application ultimately wishes to talk. So of course you want to use the STAN that will be able to communicate or near the peer you want to talk, although that may be difficult to determine. Using the STAN servers located on the public internet like stan.ekiga.net, stan.extend.com, num.viagenie.ca is usually adequate. So these available or freely available STAN servers in the internet are usually available to communicate with the peer you want to talk to. So some servers may be discovered using DNS service, SRV records, see chapter 11. An example STAN binding request is given in figure 7.9. So here's an example of a STAN request. A STAN binding request, the request contains 96-bit transaction ID and software attribute that identifies the client making the request. So here the attribute type, it identifies the one making the request. The attributes contain 10 characters, but this value is rounded up to the next multiple of 4, giving an attribute value of 12. The message length of 16 also include the 4 bytes used to include the attributes type and length. The STAN header is not included. So this 16 does not include the STAN header. So the sample STAN binding request in figure 7.9 is initiated from a client. The transaction ID has been selected randomly and the request is sent to num.viagenie.ca with IPv4 address 216.146.4, 6.55 and 216.146.4, 6.59, which is both a STAN and a turn server. So this is both a STAN and a turn server. As you can see, you have a binding request to that, and there's a binding request response success. And you can see this also the frame 1 or the first frame we have sent on the wire, or the first IP packet. So we have also a transaction ID 96 bits written in hexadecimal. So it's a random. We also have message cookie type. It's a binding request. So that's one of the message type we discussed earlier. The request contains the software attribute that identifies the client application. In this case, the request was initiated by PJNath 1.6. So this is the PJS IPNAT helper application included with Pisua. So the client software that sent it is part of a Pisua group. The message length includes 4 bytes for the attribute type and length plus 12 bytes used to hold the attributes. So here are measured in bytes, so meaning the attributes, since those are variable length, it shows here that it is padded by 4 and now it is 12. But initially it's actually just 10, right? So here the attribute contains 10 characters, but this value is rounded up to the next multiple of 4, giving an attribute value of 12. The length of pjnat 1.6 is only 10 bytes, but attribute lengths are always rounded up to the nearest 4-byte multiple. After passing through a NOT, the response is given in 7.10 here. So you can see binding success response, map address 71, etc. So figure point 10, a stand binding response containing 4 attributes. So as you can see, the response could have 4 attributes. It is in one message, but it has 4 attributes. In the first scenario, we only have 1 attribute, which is a software attribute that identifies the client making the request, and it has 10 characters. So a stand binding response containing 4 attributes, the map address and source map address attributes contains the server reflexive addressing information. So this server reflexive is we're gonna use by the client to then even communicate with its actual peer available or actual address available near to peer. The other attributes are used with an experimental NOT behavior discovery mechanism, RFC 5780. The binding response shown in figure 7.10 gives useful information to the client encoded as a collection attributes. The map address and XOR map address attributes indicate that stand server determined the server reflexive address of 71.134.182.214:33294. So since it could be stan and it could be also a turn, this XOR map and map address determine that it is actually a stan server that helped them. I mean, the turn is also a stan, came from stan. So the response and origin and other address attributes are used by an experimental facility for discovering NOT behavior. So these are the experimental written in RFC 5782. The first gives the communication endpoints used to send the stan message 216.146.46.55:3478, which matches the sending IP address and UDP port number. So the 216.146.46.55 is this, the source, right? So the first gives communication endpoint used to send the stan message. So this is where the port came from, which matches the sending IPv4 address and UDP port number. So that's the first attribute. The second attribute, let's see the first attribute. So as you can see as well, 0100 and A442. Let's see the first one. The transaction ID here, 010A442. You have the same message length, transaction ID and cookie, and the message length is only 16 for the sent or the binding request, but for this response you have length of 48, because again it has 4 attributes. So this we have response origin for experimental, and response origin as well as 216.146.46.55 colon 3478. So the first gives communication endpoint used to send STAN, which matches the sending IPv4 address and its UDP port number. The second attribute indicates which source IPv4 address and port number would have been used if the client requested change address or change port behavior. The 216.146.45.59 colon 3479 would be used as a fallback. So here it is in the other address. So the first address is the one that is has been used to send, but this will serve as a fallback in case it did not work. This latter attribute is equivalent to now deprecated change address attributes in classic STAN. If a change address port is specified in a request, a cooperating STAN server attempts to use a different address when responding to the client if possible. STAN can be used to perform address fixing as well as number of other functions called mechanism, including DNS discovery, a method to redirect to an alternate server, and message integrity exchange. So it also supports DNS discovery to redirect to an alternate server and a message integrity exchange. So those are the properties that's supported by STAN. Mechanisms are selected in the context of particular STAN usage. So in general, they are considered optional STAN features. It's not like a required. So these mechanisms are optional. It's not required. One of the more important mechanisms provides authentication and message integrity. It has two forms: the short-term credential mechanism and the long-term credential mechanism. So these are optional that you could implement in STAN, a short-term and a long-term credential mechanism. Short-term credentials are intended to last for a single session. The particular duration is defined by STAN usage. Long-term credentials last across sessions. They correspond to a login ID or account. Kind of like when you're logged in, you can do things and you're logged in forever in some websites such as Azure. Shorter credential are only for each sessions, while logging in once will log you out unless explicitly specified. Short-term credentials are often used in particular message exchanges, and long-term credentials are used when some particular resource is to be allocated with turn. See section 74.4. You can also implement this long-term and short-term in your app in case like you want to log in them forever. Even if they restart the memory, your server will remember them that they are logged in. Or it's for user convenience, but if not, then you can also choose to have them log in each time. Short-term credentials are often used in particular message exchanges, and long-term credentials are used when some particular resource is to be allocated, like turn. So long-term credentials are being used in turn, which we will discuss in the later or in the future. And a short term is in a particular usage or exchanges. The short-term credential mechanism uses the username and message integrity attributes. So those two attributes are used. Send additional for message type. Both are required on any request. So each time you request, you send message, those two attributes are included if you want to implement the short-term credential. The username gives an indication of which credentials are required and allow the message sender to use the appropriate shared password, informing an integrity check on the message, a MAC computed on the message contents. So this username gives an indication of which credentials are required and allows the message sender to use the appropriate shared password, informing an integrity check on the message, known as a MAC computed on message contents. When using short-term credentials, it is assumed that some form of credential information like username and password has been exchanged earlier. So it must assume that there has been saved username and password. The credential is used for forming an integrity check on stan messages that is encoded in the message integrity attribute. So the stan message will be overwhelmed or will be protected by that credential that is included in the message integrity attribute. So this the message integrity attribute is where your message came. The ability to form a valid message integrity attribute value is an indication that the sender holds a current, fresh copy of the appropriate credential. The long-term credential mechanism ensures freshness in a different way, using a digest challenge. When using this mechanism, a client initially makes a request without any authentication material. The server rejects the request but provides a real attribute in response. So again, the long-term credential mechanism ensures freshness in a different way. Using a digest challenge, when using this mechanism, a client initially makes a request without any authentication material. So first, there's no authentication material. The server rejects the request but provides a real attribute in response. This can be used by client to determine which credential is needed to provide adequate authentication. So the server is gonna provide a clue to the client which credential is needed to provide adequate authentication, as the client may have credentials for various services, like multiple VoIP accounts. For example, in call center and soft accounts, the client will send a message first, and then the server will then respond with different accounts of the client he can use to log in. Along with Realm, the server provides a never reused nonce value, which the client uses in forming a subsequent request. So this never reuse will gonna be like the key that will allow the client that this transaction is different because it cannot be reused, that nonce value. This mechanism also uses a message integrity attribute like the short term. So it adds so this type of request has a mandatory message integrity attribute, but its integrity function is computed by including the nonce value. Thus, it is difficult for an eavesdropper that overheard a previous long-term credentials exchange to simply replay a validated request because the nonce value is different, because it cannot be reused. The use of nonce values in authentication and related concerns are discussed in more detail in Chapter 18. The long-term credentials mechanism cannot be used to protect stan indications, as these transactions do not operate as request or response pairs. Traversal, using relays around NAT or turn as last resort method to support communication in such circumstances. It involves a relay server that shuttles data between systems that could otherwise not communicate. So if that stand didn't work, we could use a relay server that shuttle the data between systems that could otherwise not communicate, using extensions to stan and some turn-specific messages. So we will add the turn-specific messages or methods in message types and attributes. It supports communication even when most other approaches have failed, provided a common server that is not behind a NAT can be reached by each client. So this is the one property that it must observe. There should be one client that is not behind the NAT that is reachable by each client. Referring to 7.11, a turn client behind a NAT contacts a turn server, usually on the public internet, and indicates the other systems, called peers, with which it wishes to communicate. So figure 7.11, based on RFC 5766, a turn server helps client behind botnets to communicate by relaying traffic. Traffic flowing between client and server may use TCP, UDP, or TCP with TLS. Traffic between the server and one or more piece uses UDP. Relaying is a last resort measure for communication. Direct methods are preferred if available. Finding the server's address and appropriate protocol to use for communication is accomplished using a special DNS NAPTR record. See Chapter 11 and RFC 5928, or by manual configuration. There's two ways. You can use DNS NAPTR to find the server address, which is this, or manual configuration if you know the address. The client, or the address of this turn server. The client obtains address and port information called the relay transport address. So here, from the server, which are the address and port number used by turn server to communicate with peers. So this relay transport address from the server in here are the address and port number, are where the address and port number used by turn server to communicate with other peers and all the peers. The client also obtain its own server reflexive transport address. So here's the server reflexive transport address of the client. So that's the peer A server reflexive address. So you can see these are the first peer, or the peer A, and this third the peer B, and this is the client. Actually, this is the client server reflexive transport address that it obtained. Peers also have server reflexive transport address that represent their external address, like this. These addresses are needed by the client and server to perform the plumbing necessary to interconnect the client and peers. The method used to exchange this addressing information is not defined within the scope of turn. So the method that will be used to exchange this information will not be defined, is not the scope of turn. Instead, this information must be exchanged using some other mechanism like ICE that we will discuss later on in the future video in order for turn servers to be used effectively. So the mechanics for exchanging information like this will be used by ICE. So the client uses turn commands to create and maintain allocations on the server, kind of like a mapping, or whether it's manual or DNS, it will maintain in a memory for that turn to create and maintain allocations to the server. An allocation resembles a multi-way not binding and includes the unique relayed transport address. So an allocation resembles a not binding, kind of like a bind request in the stun, and it includes a unique relayed transport address that each peer can use to reach the client. Server or peer data is sent using straightforward turn message, traditionally carried in UDP or IPv4. So the server or peer data is now sent after that IC configure is sent using straightforward turn message, traditionally carried in UDP or IPv4. So this data from server to peer is carried from traditionally carried in UDP and IPv4. Enhancement, however, support now the TCP, RFC 6062 and IPv6, and also a relaying between IPv4 and IPv6. So you can also now communicate with WebRTC with IPv4 and IPv6. So even if it's in abroad because of this new enhancement. Server or client data is encapsulated with an indication of corresponding peers that sent or should receive the associated data. So this data is encapsulated with an indication of the corresponding that sent or received the associated data. For this encapsulated data to be sent whoever it's meant to. Turn support two methods for copying data between a client and its peers. The first encode data using STAN methods called send and data defined in RFC 5766, which are STAN indicators and therefore not authenticated. So this first method encodes data using STAN methods called STAN and data. So the STAN methods we discussed that in the previous video. The other uses a turn-specific concept called channels. So these channels do not use STAN. This is important because it's a small size or in small bytes. Channels are are communication paths between a client and a peer that have less overhead than the send and data methods of the STAN. Messages carried over channels use smaller 4-byte header that is incompatible with the larger STAN formatted messages ordinarily used by turn. Up to 16K channels can be associated with an allocation. Channels were developed to help some applications such as VoIP that prefer to use a relatively small packets to reduce latency and overhead. So we will discuss this in the next video, the turn, how it relates to turn, and other specific turn concept in the future video. So let's just come back to this.